I'm going to divide the presentation in 3 parts. First part's going to be this one, physical interpretation. Second one is going to be the slit experiment. And then I'm going to lead into polarization. Okay, that's what we're going to do today. And so here we have, this is the physical interpretation. What is it? And this is what I'm going to be covering. I'm saying physics is about providing a physical interpretation, okay, to a phenomenon. A physical interpretation requires an object. These are the arguments that I'm going to make. Mathematical physics does not provide physical interpretation to any phenomenon in which an invisible entity serves as a mediator. And finally, I'm going to give an example, which is magnetism, essentially 2 magnets, how they work, okay? And I'm going to show that this magnetic attraction / repulsion can be explained with another model, my rope model, and it cannot be explained by quantum mechanics. In other words, they do not have a physical interpretation. But for this, we need to know what is a physical interpretation, okay? So let's go on. We have to start, what is physics? Okay, what do we intend with it? When we say physics, what are we referring to? Are we referring to equations, math, numbers? What are we relating to? And so the first place to start is here, where you look for definitions. What are the formal definitions out there? One of them comes from the Wikipedia. The purpose of physics is to what? Understand how the universe behaves. Sounds straightforward. The problem is the word how. The word how up there, very misleading. Are we talking about a description of how something works? You know, here I have maybe a pen here, right? I let it go, right? And it falls to the table. And you say, well, how did it fall? Well, it fell at 9.8 meters per second square. Yeah, that's how it fell. In other words, a mathematical description. You still haven't told me why, the cause, what the mechanism is. And again, we also have a problem with the word why, because why, people confuse purpose, reason, with cause and mechanism. Cause and mechanism belong to physics. Reason and purpose, I call that philosophy, okay? So these words are very critical because you say how and someone understands something else, okay? So be careful about the word how. Anyways, physics, the second one there, this is from the Random House Dictionary. Physics, the science that deals with matter, energy, motion, and force. Does physics deal with energy? Does physics deal with force? These are words of mathematics. And I'm going to argue today they have nothing to do with physics. Okay? I'm not here to convince you. I'm here to argue my case. I'm in a court of law here, and you can reach whatever conclusions you want. All I'm saying, this is going to be my argument, okay? The Institute of Physics, IOP, very important institute, clarifies that this is what it means, right? Physics is about asking fundamental questions, okay, I like that, and trying to answer them by observing and experimenting. And I'm saying physics has nothing to do with experiments or observations. And here, I'll prove it to you, may I? I dropped a pen, right? I can do experiment, 100 times you want? 1,000,000 times? Whatever number of times you want. Okay, so I dropped the pen. I did the experiment. A repeatable experiment. And I made an observation. Is that physics? Or is physics understanding? Here, let me make another experiment. I'll move my arm. Okay? Is that physics? Just saying, okay, here's a phenomenon, and I can move my arm. Here's an observation. I'm watching it. I'm seeing it. I document it. I can measure, put a number. Is that physics? Or is physics understanding what causes my arm to move? And this is what I'm going to try to separate one from the other. And they have a couple questions here. One is, how did the universe begin, which I didn't like. And the other one is, how will the universe change in the future? Is this what physics does? Talk about the universe having, what physics does about the universe having a beginning? Was there a beginning to the universe? Is this a valid question? Or are we talking about, Bible here, in the beginning? And then how will it change in the future? Is this part of physics? Are we interested in what's going to happen in the future? Or is this an element of physics? And I'm saying these two first ones that come out of the IOP have very little, if anything, to do with, with physics. And here, the Khan Academy, they also say, what do physicists do? What do they do for a living? Everybody wonders this, These guys are sitting in Cambridge, Harvard. What do they do? Their physics department, what do they do all day? Just fool around with equations, write on the blackboard? What do they do? And this is what they say, and this is a very important site on the internet. It says, precisely define the most fundamental, right, measurable quantities in the universe. Okay? And the second one, find relationships between those fundamental measured quantities. Is this what physics is about? Quantities? Just numbers? Again, we're saying how, but from this description point of view, we're not saying how from an explanation point of view. We still don't understand what the mechanism is by following this. If this is what physicists do, they're not physicists. Okay? That's going to be my argument. Okay? Yeah, you don't have to agree with me. I'm just saying this is what I'm going to put forth. Okay, am I doing physics when I ask these questions? And here you have one, by what mechanism does a magnet attract another? Is this an issue of physics? Does physics deal with this issue at all? What causes a spoon to fall to the floor rather than to the ceiling? You would think it's a question of physics. I mean, I think it is. I don't know about you, but you got to think about this, right? What is electricity? What is happening inside a wire? You got a wire, you touch it, and well, you don't want to touch it, but if you do touch it, maybe you don't have to worry anymore about physics. Something happened there, right? Okay, is this a question of physics? What causes stars at the edge of the galaxy to travel faster or just as fast as those near the center? These are questions of physics. But none of the previous definitions, address this. They're just saying we're going to quantify it. We're going to give you a quantity. So I don't have a mechanism. All I have is a quantity, a number, an equation. That's a description. Okay? The Khan Academy says at the end, to be honest, it's really difficult to define exactly what physics is. I love that one. Like, we don't have a slightest clue what we're doing. Physics keeps changing. And yes, physics does keep changing, but in the wrong direction if we're going to follow what these people have done in the 20th century. Max Born said in a book he wrote in the 60s, he said, physics has become more abstract. Well, abstract is the opposite of physical. So don't call it physics if you're going to do abstractions. Call it abstraction, Department of Abstractions. That's what you should call it, not Department of Physics. What is science? Science, rational explanations. That's what science is. You have to explain a phenomenon rationally. I always give the example of a magician. Cuts the lady in half, 2 pieces. Curtains closed, curtains open. Lady comes out in 1 piece. So what is physics? What is math? Well, the mathematician would tell you, well, he cut it in so many strokes, 10 strokes, 1 stroke per second. She had 2 pieces, now she's in 1. That's numbering, that's equations, that's just quantities. No, I want to know how the magician did the trick. That's physics. So we have 2 words there, rational and explanations. So all we have to do is know what an explanation is, what rational means. And let's go with explanations first. Here we have explain or explanation, illustration of the causes and mechanisms that underlie a phenomenon. That's physics. That's what physics does. What does mathematics do? It just describes an equation that synthesizes how an object behaved. You can say, a lion ran at 60 miles per hour. Okay, that's just a description. You still haven't explained anything with that number, with that equation, with whatever you put forth, okay? Here's what rational is. I usually take it in reverse and say, I try to define what irrational is. And my son corrected me some time ago, says, well, you don't want to call people irrational because they get upset. And so we don't, we try to be impersonal. We say, look, what we have to say here is the theory is rational. I'm sorry if you take it personally. Okay? So the main one, converting a concept into an object. You convert a concept such as love, you treat it as a physical object, now you begin to move it around, you forget, that you were dealing with a concept. So you take energy, and you say, I transferred energy. What do you mean you transferred energy? What did you transfer? Energy is a concept. In fact, it's an undefined concept. Nobody hasn't been able to find what energy is, the concept. But you're going to transfer this? I mean, I can transfer a pen to you, I can transfer a dog to you, a tree, whatever, but I cannot transfer a concept. And so that's the main one, converting a concept into an object and then treating it as an object and moving it around. That's the first one. Second one, you use your words inconsistently. You don't define your terms, or whatever you define, you use them inconsistently throughout your presentation. Very famous case, the word point. The word point is defined usually as, they say, what is a point? And the guy said, well, here it is, and he puts a dot on the board. Say, okay, here we have a little dot, and okay, that's a point. I understand that, I can see it. And then the guy never uses that. And he always uses, oh yeah, see, we have all these locations or all these numbers. What do you mean numbers? I thought it was a dot. Well, yeah, but that's only to represent the point. So it's a pictorial representation of a point. Then what is the point? I mean, if that's the pictorial one, I don't care. I want to know what the point is. And if the point is going to be used as a number or as a, as a location, then we have a conflict there because he's not using his terms consistently. Theory doesn't follow from the assumptions. I give the example, the prosecutor presents a knife, and then his theory is about, poison, how the person was poisoned. One doesn't follow from the other. Describe and pretend to explain, especially magnetism, I'm going to cover in a minute. People tend to say, oh, I know how a magnet works. Oh, okay, how does it work? Well, you have all these domains, etc., and you have all these electrons that move in each magnet, okay? So the electrons are moving around, they're spinning around in the same direction. Okay, so where you've described, you haven't told me how the spinning of one electron pulls on the spinning of another electron. Here I have a situation. Two balls. Let's consider these electrons. So this one's spinning, and this one's spinning. Fine. This one's on this magnet, this one's on the other magnet. What's the mechanism of attraction? This is the issue. How does this one attract that one? Don't tell me they're spinning, that's a description. Fine, okay, they're spinning. And what is the mechanism of attraction? And they don't have that. And also the last one, formulate cause and mechanism in terms of reasons and purpose. Why is there something rather than nothing? That's a question that doesn't pertain to physics. Not if it's formulated in a way that says, why did God make something rather than nothing? Why did God make the speed of light 300,000 kilometers per second? Well, I don't know. He had a headache? I don't know. I mean, that's a reason. That's a question of purpose, not a question of what is the cause, what is the physical mechanism. So those are two different things. And again, we tend to confuse these and think that mathematics represents physics and vice versa. It's not the case. Okay, so here's my definition. Physics, rational explanations of causes and mechanisms. That's what physics is about. And if we're going to explain, we're going to have to use objects. As far as I know, you cannot do physics without objects. If we bring God in, good old man there, he wipes all the matter of the universe, no more matter. What physics is going on? What are we seeing? What's happening? There's nothing there. The only way you can have phenomena happen is with objects. It's as simple as that. Here we have the researcher, someone who carries out experiments, verifies what others have observed, brainstorms explanations, does calculations, makes predictions or intelligent guesses, observes phenomena, and verifies his hunches. Okay, that's a researcher. A researcher is a detective seeking clues to the workings of the universe. And that's fine. That's a noble, job. You go to your basement, you say, I want to know about this. I'm going to run an experiment. You can do anything you want. But that's not a physicist. That's not a scientist. The scientist is the guy who comes to the conference and gives you an explanation of something, how it works, a mechanism that you can bite your teeth into. Doesn't mean you have to believe it. Just means now you understand what this guy has going through his mind. That's all it is. And that's why I'm saying the theorist, the physicist, right? This is the real scientist, an individual who communicates how something happened. The purpose of a physicist is not to persuade, convince, convert, and recruit. I'm not here to twist your arms. I'm here to give you something objectively that you can take home and say, oh, okay, now I know another version of how this universe works. Doesn't mean you're going to believe it. I can bring angels and say, look, this thing works with angels. Okay, I know what's going through your mind. I see how you're explaining it. Doesn't mean you have to believe it. Okay? And what he does, the task of a physicist is to explain a mechanism objectively so that the listener visualizes what caused the event to occur. Okay? Physicist is a movie director. You should be able to make a movie, if you're a physicist, you should be able to make a movie of your theory, put it on the board for people to watch and understand the mechanism just by watching the movie. You want to know how a car works? Well, you can put that in images. You can say, look, here's the tank, here's the tube that takes the gas to the front of the car, it goes through the carburetors, etc., and this is how it moves the wheels. You can put all these parts in a movie and more or less, give some background information, and the guy can understand how a car works. Well, now we do the same thing with invisible entities. You say, well, here you have two magnets. One magnet attracts the other one. Again, very simple, much simpler than a car for that matter. So how did it do it? What kind of magic does it do it with? Well, you have to fill in the blanks. You have to put something in between those two magnets. Otherwise, you're using magic. You're putting spirits in there. Okay? And so that's what a physicist does. He makes the invisible visible. Suddenly you can see what you could not see before. And, with us, we do a little trick. I think I can do it with this. I'm going to do a magic trick. It's going to blow your mind away. Never happened before. You'll see it for the first time in human history, Now, between my mouth and the paper, did you see anything happen? Did you see anything there? No. And the issue is that we are not able to see everything. That doesn't mean that there's nothing in there, okay? And the way we simulate this is by putting particles. We say, well, this is made out of oxygen. Okay, what is an oxygen? It's a molecule. What is an molecule? Well, it's made out of, atoms. Okay, and so on and so forth. But you always have a physical object, some little ball there that you can't see, but you can imagine, say, okay, I see what you're saying. But to say that there's absolutely nothing between two magnets, then you're putting spirits. You're putting magic in there. You must put something between two magnets. Otherwise, you have not explained the mechanism. Okay? And I arrived at the golden principle, physics requires an object. And a simple principle is so profound that it really should blow you away if you really understand it. Thou shalt not do physics without an object. You can't do physics without an object. What would there be happening? So if there is something bringing two magnets together, there's something there, and we're going to call that an object. It's something that has shape, something that's in there, and that is producing this effect. We just don't see it, just like we couldn't see the air, but something is in there, okay? So now, everybody knows what an object is, right? Well, not really. In 10,000 years, no one has defined what an object is, at least for the purposes of physics. And here's the mathematical version, okay? They don't look at objects. They say, well, we're interested in physical quantities, whatever that can possibly mean. It says, is a physical property, etc., etc., etc. Okay, so what is a physical property? Well, any property. I love that because they define a physical property as a property. They use a synonym, but he says that is measurable. Okay, something that is measured. They want to put a number there. They want to put meters, whatever. Something that is measurable, or pounds, or whatever. Right? In physics, a physical system is a portion of the physical universe chosen for analysis. So you take a chunk of the universe and you say, I'm going to analyze this, and that's going to be a physical system. What's in there? Physical quantities. What is a physical quantity? It's a physical property. Everybody understood perfectly? Okay, that's the way it works. It's just a bunch of words that they created. It doesn't really take you to the bottom of it. And they finally they say, well, in physics, a physical body, this is from different websites, by the way, physical body or physical object, right? And listen to this. Is an identifiable collection of matter What they're saying is you take a bag full of marbles, and all those marbles constitute a physical object. Okay, that's what they're saying. An object, a dog is not a dog, he's just a bunch of atoms. Okay? Same for a tree or for whatever. Which may be constrained, maybe. It's like, maybe, you know, it's like a secondary issue. May be constrained by an identifiable boundary. So some objects have boundaries, some don't, so it may be concerned. Obviously, they haven't thought about this very long. And it can move, essentially, right? So if the object has a bunch of marbles and it's constrained by some kind of, you know, skin, and it moves, now we have an object, okay? Easy. Okay, and I'm saying these are really the criteria that you can take out of all that. You can say, look, if you look up the word object in the dictionary, they say it's see and touch. Anything that you can see or touch. Okay. Other people have come to me with the fact that it's a volume. Others say it's a mass, whatever has mass. Others say that which can move, and what we just heard, you know, what it's made out of. And I'm saying none of those are valid definitions, scientific definition. An object is that which has shape, stands alone. That's what I'm going to use today, that definition. Okay? We have to distinguish it from what a concept is. Concept is different than an object, first because it doesn't have shape. That's the first one. But that's just like a rule of thumb to be able to say, okay, I take every word in the dictionary. If it has shape, I'll put it under objects. If it doesn't have shape, I'll put it under concepts. But otherwise, it's just a word that includes or embodies two objects. Every concept that you can think of has embodied in it at least two objects. Why? Because the word concept is a relationship between two objects. It's a relationship. Okay. Okay. Here we have the word energy. Is energy an object or a concept? Widely used in mathematics. And here you have, you know, all this this smoke going on. Is that energy? Well, you know, we have Mr. I don't want to put words in anybody's mouth, so I'll just use Richard Feynman's words. He says, it is important to realize that in physics today we have no knowledge of what energy is. So they have no idea what energy is, but everybody uses this word. And that makes you stop and think. You know, this is a very important word in physics, in mathematical physics. Mass. Here we have a couple guys, Edwin Taylor and John Wheeler. John Wheeler is a very famous guy, at least. Many people know him. He was a student, by the way, of Richard Feynman. And nature does not offer us any concept as the amount of matter, which is what we're taught in high school. You go to high school and they say, matter, what is mass? That's the amount of matter. Oh, okay. You know, it's like you count marbles again. And then here these guys says, you know, when you get to college, we're going to tell you the opposite. It's not the amount of matter. In fact, there's two kinds of mass. One is inertial mass, the other one is relativistic mass. Inertial mass has to do with the quantity of matter, supposedly when they use it in this context. And in another context, they're going to use something else, which is how fast you speed up something. You know, you speed up the elephant, he's got more mass. And it came out of the speed, not of the amount of matter. Okay, so they don't have any idea. They just use these two concepts. Okay, time, what is time? Well, we don't have any idea what time is. According to the NIST, the definition of time is the designation of an instant on a selected time scale. What is a time scale? An agreed upon system for keeping time. So we made full circle. That's how these things work, okay? What is time? We don't know. Of course you don't know because you haven't defined it. That's why you don't know. But all of these are concepts. But the main concept I want to deal with today, because I'm going to be giving as an example magnetic fields, is the word field. And here we have all kinds of fields, okay? We have the electric field, and we have the magnetic field, and we have the gravitational field. You know, all these nice fields that we've invented. So what is a field? Well, there you have it. You have a whole bunch of vectors. Those arrows are not Indian arrows. They're vectors. And they have magnitude and direction. That's what a vector is, magnitude and direction. And they come out of that center point. That center point is something real. So that little, like in the first drawing there, the blue one, and the red one next to it, those are like heads of something, okay? Some little electrical head. So that is tangible. That is a real object. Everything that comes out of it are just vectors. And what is a vector? Vector means that it decreases as it gets farther away from the source. Okay? So you get the magnetic field farther away from a magnet, it gets weaker. You get an electric field farther away from a electric head, gets weaker. You get gravitational field farther away from, in this case, the planet, it gets weaker. That's all the word field means, that there is a region around a physical object that extends to infinity. And all you can do is give values along along the vector. So if you draw a straight line from the center of the Earth out to the edge of space-time or whatever the edge of the universe is, all they say is the field extends all the way there, but ever weaker, 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 and weaker. That's all a field is, just a bunch of numbers that get weaker away from a source. That's a concept. Field in physics is a term for region. That's all it is, a region around an object, okay? And that's under the influence of some force that can act on matter within the region. Okay? So all you have is you have something else coming close to that region, and it's influenced by this invisible, unknown thing called a field. That's all it is. But then if you look at the definition, field is a region of space. You look up the word region, it's a portion of space, and you look up the word space, it's the infinite extension of field. So you have the full circle there. That's what it is. We have no real definitions for these words. But the important thing is that field is a concept. Okay? And the question is whether there exists, like in the case of magnets, a standalone field. I mean, we can all recognize what a field is when you have a magnet. You say, okay, I sprinkled some iron filings there, and then, gives you the shape of the so-called field. Fine. Can we have the field without the magnet? Can I bring a field to the conference and say, look, this is what a field is, a bunch of vectors, like we said, that's what those are, vectors, by the way, with magnitude and direction, that's all they are. And no, you can't. You can't bring, vector. I cannot bring a vector to you. So are we talking physics, or are we talking math? And again, this is something you've got to keep in mind all the time. Okay, here you have different kinds of, again, fields. And the important thing I want to show here, and look at this, see, look at the arrows, look at the arrows. This is important. They go into the South Pole and out the North, in all cases, okay? So no matter what magnet you get, that's how it's all represented. Now this is convention, okay? The lines exist, in other words, there is some kind of flow. The word is flow. But they don't know what it is, and they just say, look, we're going to call the place where it goes into the magnet, we'll call that the south. The place where it comes out, we'll call it the north. That's just convention, okay? But the point is that there is some kind of flow of something, whatever it is, and it follows these vectors. And they have magnitude. They get stronger near the magnet, weaker farther away from the magnet, okay? That's important to notice, okay? And why is this important? Because I'm going to show you how a magnet works and show you that there is a physical interpretation for this. You don't have to believe my physical interpretation. I'm saying I'm going to try to explain this phenomenon that you see there. Goes into the South Pole, out the North. Okay? Here we have two magnets. Okay? They attract each other. Magic. So what do we know? Let's put a field in there. So, how did the field do it? Yeah, okay, so it's got a field. Okay, then what do we do with this? Have you understood the mechanism of how a magnet attracts another by putting the word field, by putting something around it? No, and obviously you can't. You cannot understand by putting the word, in fact, the word field hides more than what it, reveals. Remember, it goes into the South Pole, out the North, right? And here you have the flow. So I'm going to spend a little time on this one. You're going to see at the top, this is a coil. Okay? You have a coil, and you have the flow of the magnetic field around a coil. A coil that has magnet, because it's electrified or whatever, that's the flow of the so-called magnetic field around a coil. And you can superimpose a magnet up, on top of that in the center, right? And it's going to have the same pattern of the field. The field's going to have the same pattern as a coil, whether it's a magnet or a coil. Okay? And I'm saying it looks like, what I showed there a second ago, you'll see it again. Here you can see on the top, it goes to the right, it's clockwise, and the top part of the coil would go clockwise, the bottom part would go counterclockwise. Look at the arrows, okay? If you look at the arrows, it goes into the South Pole, there's the magnet superimposed on it, and out the North. That's the pattern that field, a magnetic field leaves, either on a coil or on a magnet. And I put two tanks, army tanks, and they're facing each other, okay? And you saw those tracks that go around, and that's essentially the flow of what you see in a magnetic field. It's like if you put two tanks one against each other upside down, right? And whereas in the top one you will have clockwise, the bottom one will have counterclockwise. Okay, look at the flow. That's the flow of a magnet. Around the center of a magnet, okay, and out the other end, the south end, it's just like that. So if you look at each one of the pictures, this is a little bit of brainwashing I'm giving you here, okay, but keep in mind, this is the flow of a magnet. That's what's happening inside a magnet. And this has been already tested and verified and whatever. So nobody will disagree with this, with the flows, okay? But that's what it is. And if you look at it, that's the flow of the field. Something is moving in there. And that something, it's important to know, James Maxwell said, what's in there? What is it? What is a field? He says, there is matter in motion, matter in motion. He says, I don't know what it is, but there's something moving in there. And the same thing, more or less, that was said by Faraday before him. He says, a magnetic field, I cannot imagine all those lines of force without some physicality in there. He just didn't accept that was just the spirit or whatever. He said, there's something there, I just don't know what it is. Okay? And so I'm going to put something in there so that you can visualize the same mechanism. We have to explain this pattern. Okay? We have to explain the flow around a magnet. Okay, and so this is what I'm saying it is. You take two guys, put them on top of a magnet. You take two guys, put them on the bottom of a magnet. They swing their ropes around, and you can see they latch on because they're both swinging. The guys on the top are swinging their ropes counterclockwise. The two guys on the bottom are swinging their ropes clockwise. And those ropes are going through the center. And you can see the two magnets there. You can see the one that has the south and the north. The the ropes in this case, go into the south end and come out the north. When you put these magnets together, you can see what's happening. They latch onto each other. If you look at just the blue part, okay, let's look at the blue part only. The guy on the top left, he's swinging his rope counterclockwise, and it latches onto the guy on the right, who also swings his rope counterclockwise. Look at the guys on the bottom. They're both swinging their ropes clockwise, and again, they latch on and pull each other. So I'm saying it's a very simple mechanism. It's just, this guy's going like this, and the other guy's going like that. It goes into the South Pole, out the North Pole, okay? And where if you put north against south, you get this situation where these two are going on the top are going this way, and the two on the bottom are going that way. Let's see if we got it right. Okay, so you can see the pattern that matches what we see in magnets and in coils. It's exactly the same pattern. So there's no reason to say that this does not at least simulate what we see with magnets. Okay? Here we have the same two little guys on top. They're swinging their ropes. Now we're going to rotate the magnet on the left upside down. I'm just going to turn them around. You can see there what's happening. And when you turn them upside down, the guy on the left still remains counterclockwise on top, and the guy on the bottom still remains clockwise on the bottom. And you can watch it a couple seconds to verify for yourself that is the case. And that's exactly what we verify in a magnet. If you turn a rectangular magnet, if you turn it upside down, it'll still be north against south. Nothing changes. And that's why you can see it here. You see that with the flow of ropes, nothing changes. It always remains counterclockwise at the top, clockwise on the bottom. Okay? What happens when we turn them now 180 degrees? One of the magnets 100 degrees, and we put north against north or south against south. Well, we know what happens. They push each other away, right? And here it is. You'll see it here. We're going to turn this guy around 180 degrees, the guy on the left. There he goes. And now you can see that the guy on the top left, he's clockwise. He's no longer counterclockwise. And the guy on the bottom, he's no longer clockwise. Now he's counterclockwise. And what do? They push each other away. They swing their ropes right? And they're clashing, pushing each other away. Okay? Simple. Very easy to understand, just the mechanism. It doesn't mean you believe it, it just means I've been able to imitate the mechanism, okay? So what are the questions that people ask at this point? Well, they say, well, what are those ropes made out of, you know, and why do they do this, and where do they come from, and, you know, they've got all these kinds of questions. And the answer to all those questions is the same. It's beyond the scope of this presentation. Right now, I just want to show that with this mechanism, with these ropes, I can produce attraction and repulsion in the way that I've just showed. I've illustrated it. Now let's try it with particles. Can you do it with particles? I mean, I'll give you all the time you want. You know, are you going to throw particles at the other guy? How do you pull a magnet towards another with particles, with discrete particles? And you cannot even imagine a mechanism. So the only thing that I'm trying to say today is, yeah, we can go into what is a rope made of, why are they swinging? We can go into all those questions. But right now I just want to concentrate on the mechanism. I've explained the mechanism with objects. I'm saying it's a rope, it's a physical object. It's a very tiny, invisible object. And these ropes swing around, and I'm producing the mechanism. I'm simulating first the field around a magnet first. And second, I'm producing attraction from a distance and repulsion also from a distance. Okay? So that's the point of the presentation today. And so here are the conclusions. Physics is about providing a physical interpretation to phenomena. A physical interpretation requires an object. You do need objects. You can't do it with concepts. You can't move concepts around. Mathematical physics simulates all invisible phenomena with concepts. They use energy, mass, force, time, field, right? And mathematical physics does not have a physical interpretation for any phenomenon in which an invisible entity serves as a mediator. You will not see it. And of course, that's why today we have no explanation. We have description, but we have no explanation for how a magnet attracts another. I do. That's it for that one.